Thank you for responding there. It's always good to know I'm heard. You never know with tech issues and so on. All right, so I think I'm going here. Screens shared. Things are recording. Oh yeah, there we go. All right, so this is the lesson from Friday, if I recall correctly. 354, if you looked at it and are freaked out, I apologize. I meant to move them to a future lesson, and I did move them to a future lesson, but forgot to actually get rid of them from this copy of this lesson. So that's 354, 3 and 4 for our parallel plates when a voltage is applied, and we just haven't looked at that part yet. This section we're tackling, the textbook covers a whole bunch of stuff and kind of mishmashes it all together, makes it really confusing to distinguish between things that are unique. So I'm separating it out. So the idea of parallel plate, just a charge on them, where voltage was applied to build up charge, but then they're just sitting, like the charge is just there, no more voltage connected, is what we've covered so far. And that these questions aren't to do with that. They're to do with when a voltage stays connected. So you'll find, I think, that these questions were more concept, not as mathematical. And then these questions down here, the 1 to 7, got into the more mathematical ideas. Any questions about any of these?
I don't have a question about like one of the questions in specific, but what does the little like fish symbol mean? Like you used it in question 7.
Fish symbol.
It's like
infinity maybe?
Something
Infinity maybe?
Like that. Like you have E something.
So that means in that scenario. Okay, that means proportional. That means proportional. So that just means that like in what do I want to say here? So they told us in parallel plates with charges built up that basically if this means if Q is multiplied by 2, then the field would be multiplied by 2 also. It means proportional. Okay, so this thing here means proportional.
Okay, thanks. Yeah, that makes sense.
So they had said that in the wording that if you have parallel plates and you've got a bunch of positives here and a bunch of negatives there, right? If you multiply the number of charges on each plate by 2, then that leads to of course that leads to the field being twice as strong. That's what that means. So yeah, we've seen that before where we had, say, like F equals ma, right? Basically, we'd say the amount of acceleration is proportional to force, right? Because if you push twice as hard, you get twice as much acceleration. Or recently, electric field force, we had K/Q over R squared. When we looked at that one, we said, well, how much force would there be if you increase one of the charges? And be like, obviously, we said, well, if increase one charge value, you're gonna get more force. Same as with gravity. If you have more mass, you're gonna have more force. So we said like proportional to Q, proportional to Q. I'm not sure if I used the symbol there or not. If I did, you might have just missed it because there's so many things going on, right? But no worries. And then we had proportional to 1 over R squared. And those observations, when a scientist back in the day was looking at what happens to electric force with more charge, they found that it was directly proportional. More charge means more force. Same for both of them. And then they found, it was related to the inverse square of the distance, which would have been trickier to figure out. And that's when we saw. Just getting this right here. Yeah, we saw that they would have ended up graphing eventually by trial and error. They would have graphed eventually by trial and error Q, the product of Q and Q divided by R squared. And if they did that, they get a straight line. And then that straight line shows that there's a known relationship basically at that point, that FE over QQ over R squared is equal to a constant, right? And that constant turned out to be the K value, the 9.0 times 10 to the 9, which is kind of neat, right? Like I definitely don't recall seeing this when I was in school, and so I always kind of wondered, like, where's that 9.0 times 10 to the 9 come from? It literally just comes from measuring how much force there will be for two known charges at a distance apart of r, of r. And so if you graph that force as a function, the value of the force depends on, it's related linearly to q times q divided by r squared. So that's all that proportion. So I've gone overboard in answering your question, I think, David, but like it's all related to that little proportional symbol. So that's it. What else? Anything else? So we had like I said, the more concept base ones where like the first question there has a little bit of a trick where it says like, what the direction, next set of questions. Yeah, it says like, what's the direction of the electric field? And so notice they tell us straight out that the negative charge, if this is the one, one sec here. I have it listed as a positive charge there, but did they tell us it was a negative charge? Yeah, I missed listing the little minus sign there in my solution. But they tell us that it's a minus to the left. And so later on here, I say it makes a negative charge go to the left. So basically what you're thinking there is, so a positive would go to the right. So would go to the right? And so that means that the electric field is to the right. So that's, we get into some mathematical calculations in this question, but also that concept question about like the direction. So try to follow through on these solution sets thoroughly and pick up those little kind of nitpicky details about what the direction's defined as and how they show things. But these ones get pretty easy, I suppose, right? It's just what happens is, you read a question like this and they say at a certain point in electric field, the magnitude of the electric field is 12 newtons per coulomb. And to me, that's a loaded statement. You got to recognize that they're telling us magnitude of the electric field, right? So magnitude of the electric field. You have to realize what they're talking about there is they're talking about field strength, right? They're talking about strength. And we know that fields are about how much force. So it's like, i.e., we're talking about how much force. And then basically that's when you sort of have to recognize like, okay, what's the equation we have to do with that? And that's our Fe over Q. It's our force per charge, right? And they're saying magnitude. Right? They're saying magnitude. So in here, I should have had that. It's a thoroughness thing. Basically, you notice that there aren't any directions involved, and I did point that out there. So I kind of followed up by pointing that out rather than necessarily having the magnitude symbol in there. But it could have been like this as well, right? So it would have been, I suppose, like that if I were, But obviously, I was firing through a bunch of solutions and tiny little things might not make it in every spot, but that's fine. Like, it means the same thing once you follow up here. So yeah, but just like that, I think that I have to encourage you to be really thorough and careful about what all of these different concepts mean. Okay, because so far we've talked about electric force, which was just Fe equals KQQ over R squared that I wrote down here, right? So we've got that main. Yeah, in here. Anyways, yeah. So the KQQ right there, KQQ over R squared. We've done that one, and then now we have this weird new one where we're talking instead about just about force, we're talking about force per charge, right? So now we've got this new formula here of the force per charge, and then if you put the KQQ over R squared in there, then you end up with another version of curly E, the force per charge, where the Q's cancel out, right? KQQ over R squared per Q. So one of those Q's cancel out. Remember, one of these Q's, this is the one that's like causing the electric field. I'll just say E field for short, EF. That one's the one's causing electric field, and then these ones that are canceling out are the ones that are like feeling the effects of, right? Feeling the effect of the other charge's electric field. Anyways, so there's another version of this equation that's kq over r squared. So when you're looking at doing this question, how did you know to use fe over q instead of kq over r squared? Well, it's because they gave us the force value, right? They actually gave us the force. So the number they gave us is actually the actual force itself versus in this one, of course, this formula here, you can tell we don't have force. We have force per charge and so on, right? So anyways, I hope that helps a little bit. Just I really want to encourage you to stay on top of this, because the electric field, electromagnetism unit overall can start to seem like a bunch of really mysterious symbols that have no meaning, like curly E. But as long as you establish firmly in your brain so that as soon as you think of magnitude electric field, you're thinking of strength, you're thinking of force, you're thinking of curly E, those need to be linked in the forefront of your mind right now, so that it's obvious. Otherwise, it's a whole bunch of mystery. This is the type where they've given you a distance and they've given you a charge and so on. So now we're talking about the kq over r squared. And I did put a reminder there like that. Remember, that comes from knowing force per charge. Oh, okay, force per charge, equation version. Plug in numbers, see what you get. Okay. These are vectors. So the next question, you calculate force per charge based on the effects from two different charges, and then they just add up vectorially. Vectorially meaning, of course, one's positive, one's negative, so it essentially becomes a subtraction. That negative symbol there, again, is showing that it's an attraction situation. Yeah, it's an attraction situation. I didn't write that in, but that's an attraction situation. And so you can see that would be to the left. A positive test charge would be attracted to the left. So I jot that in there as well. This means attraction. And so then based on the geometry of the situation, this thing is getting attracted, overall. And you can tell like it's certainly here, even though this is the smaller charge, it's super close in comparison to the 50, right? So the bigger effect, the bigger overall effect for that location is an attraction effect. So when there's two-dimensional geometry involved, this solution goes through, how to actually add those up and, look at the components and so on. I put on there that the components cancel out because of, it's an equilateral, or whatever the situation was, I forget, but you can tell it was symmetrical. So the angle to the left and the angle to the right were the same. And so it was a bit simpler numbers for the two-dimensional because all you had to do is add the two vertical components. So all of those solutions are all worked out, and I'm just hoping and encouraging you to use them and learn from them and with them. It's not I'm encouraging not to think of your homework as like a blank page that you're supposed to be able to just do from scratch. No, like the solutions are there to help you learn along the way. So any other questions before I move on to electric potential energy? No? Okay. So just recap, like we've looked at electric force, we looked at force per charge. Today we're going to look at in this lesson some new stuff, right? Some more electric concepts that we have to understand and be able to use for this course. So just to get started here, let's think about electric potential energy concepts in general, right? So in class I would have had magnets and we would have played with them, right? But if you have magnets nearby or later on you could do it or whatever, but if you had a pair of magnets, you can sort of picture them like repelling one another, and you could think of those as like charges. So if you had that's fine there. That's all I need to say that part. So when you push two like charges together, you have to actually like push to get them to go together, right? So you're doing work on the system to push them together, and it gets harder and harder to push them together, which you're familiar with if you've ever played with magnets. If you haven't, my goodness, go grab some magnets and play with them. They're kind of fun. So if you think about potential energy, right? And you're actually adding energy to the system by pushing them together if they're repelling, right? And it says, what does this mean with respect to electric potential energy? So we're adding energy to it. Do you have to do work to move them further apart? No, because if you're holding them together and they're repelling, you don't have to do work on the system to let them repel. You just, if you let go, they would just fly apart. Now, in reality, of course, they'll flip around and attract, of course, right? But if they were held in a certain orientation so that they're repelling, then they could repel along a track or whatever, held from stopping them from flipping around and attracting, they would push away on their own. So we're trying to think about what the implications are for how much energy there is in a system as we go through this. And I'm trying to work towards something here. So when you push two opposite charges together toward one another, do you have to do work? Does it get harder? Oh, two opposite charges. Sorry. So when you push two opposite charges towards one another, what kind of work do you have to do then? Well, as you go closer and closer, you're not pushing them together. You're actually kind of holding them from slamming together, aren't you? Right? So if you think back to grade 11, you're actually, I'm visualizing here right now, my left hand, helping you, trying to help you visualize. I'm holding my left hand and my right hand, and I'm picturing two magnets in each one, a magnet in each one, and they're attracting. So picture my right hand coming in towards my left hand, okay? It's going to attract more and more. So my right hand, would actually have to be pulling away from my other hand in order to stop them from slamming together, right? So as they're coming together, it's harder and harder to not have them slam together. So I'm actually pushing the other way as I bring them together. So in that case, that means we're doing like negative work, right? My hand is moving to the left towards my left hand, but I'm actually exerting a force to the right to stop it from slamming in place, slamming into the other one. So we're getting the idea of like a negative energy situation in that scenario, in terms of the work done, at least anyways. So when working with two like charges, which way would you have to move charges to give them potential to move? So if you're looking at two like charges, do the magnets have to be close together or apart from each other in order to be able to move on their own the most? Of course, they'd be close together, right? If they're close together, they have energy. They're going to move on their own. If you let them go, they're going to repel. With opposite charges, you would have to have them apart, right? So that when you let go, they would come together. So the idea that if there's energy potential, if there's energy available to make the magnets move, what's the scenario there? So you can tell in an attraction situation and in a repulsion situation, they're kind of the opposites of each other. In a repulsion situation, you've got lots of energy when you're close together because they can repel. And with an attraction situation, they have lots of energy. You have energy when you're apart from it because then it'll attract and release that energy. So we're going to be talking about positive energy versus negative energy and so on. So what happens when the charges get really far apart? Okay, so if in either case, if the charges are really, really far apart, so you have two opposite charges that want to attract, but they're like kilometers apart, they're not going to attract. They only start to attract to each other on the table or in your hands when you get them within a few centimeters usually, right? So that means that if you're really far apart, then there's no potential energy to move. You're at a zero potential energy state. Okay. And then these are just ideas for now. We're going to itemize this all with graphs and thorough discussion that should make this make sense. But zero energy to attract. And also, if two repelling charges are super far apart, nothing's going to move if you let go because they're so far apart, right? So if they're infinitely far apart, then there's no energy in both cases. Okay. So I want to remind you of, I'm going to tell you about a gravitational potential energy concept that we haven't done yet in this course. But basically, what I'm saying to you already there is that at infinity, potential energy is 0. So we're just doing this course the other in a different order. And so when we do the gravity later on, it'll be like, hey, remember, just like with the electric forces, rather than the other way around. No big deal. So electric potential energy, right, is the energy stored in a system of 2 or possibly more, but it's simplest one is just 2 charges that are a distance apart, or distance r apart. Okay, so there's a new concept for you to think about. So we talked about electric force, we talked about force per charge. Now we're talking about electric potential energy, energy stored in a system to be able to do work or whatever. So the energy is stored, since if there's an electric field, there's a force, and forces can do work, you know, so that you can certainly get the idea that there's force in the situation. And so there's energy stored in the situation. There's potential energy, just like a brick on the top shelf that can fall and hurt, you know, slam into your foot. It has potential energy because there's a force of gravity. Here we're talking about charges that have a potential energy because there's an electric force. All right. What do we got next part? Think of the activity on the previous page. Yeah. So if we bring 2 like charges together against a mutual force of repulsion, it takes work. So the energy, the work done in bringing the situation stores energy in the system. So this is what the graph would look like for energy versus distance apart. Okay, so as you bring an object or like a light charge, right, when there's a repulsion situation, as you bring it closer and closer, so this is repulsion. So in a repulsion situation, you've got positive energy stored. You're like pushing on the magnets or the charges. I'll say magnets next time we talk about this, I'm sure, later on. But anyways, it's a repulsion situation. So you're pushing in the direction you're actually moving them, right, to store energy in the system. And so the closer you push them together, the more energy is stored, the more they'll be able to repel when you let go. All right. So that's positive energy stored. But notice here, the idea of going out to infinity eventually, right? At infinity, the energy equals 0. And then the attraction situation. This is kind of the weirder one, but the attraction situation is that as you push them, as you bring them together, you're actually holding apart. So you've got a positive and a negative. Let's actually use a positive charge, and then let's start over here. I'm going to say let's use a negative charge. So we've got a big negative charge, right? And you've got the little positive test charge nearby. And so as you bring this close by, you're actually going to have to hold it back, right, in order to stop it from from accelerating. In fact, we could look at it as like there's an electric force on it, and there's an applied force on it, and then we've got constant velocity. And remember from grade 11, if you have a net force of 0, then you can have constant velocity, right? So you can see you'd have to apply a force backwards on this thing as you bring it close together. And so there's negative work being done. The negative energy is actually getting more and more negative energy. So yeah, we're talking about negative energy. And I am saying here, just like in the gravity situation, so it takes energy. So let me pause for a second here before I talk about this part, right? But I'm going to help you understand why this is negative energy. In an attraction situation, we've got negative energy, okay? So picture either with gravity or with attractions of opposite charges, it's the same thing. You have to separate those, you're doing lots of positive work, right? So let's go back, let's redraw this over here. We've got the negative charge, and we've got the positive. What do I have to do to move this thing to infinity? Right? I'd have displacement this way, and I have force this way, right? Applied force this way. And so you can tell that I'm doing positive work, right? So I am doing positive work, and so I'm adding energy to the system. Well, eventually I'm going to add enough energy that I'm going to get to zero energy. If I'm adding to a system and eventually I get to zero, what energy must that system have had? It must have had a negative energy, right? So the system itself has negative energy. So let me write out with attraction situations. So with attraction systems, there is negative energy. And we're going to see this again with gravity. It's the same thing. If you move an object far enough away from Earth, it won't come back. If you move it to infinity, it just won't come back. So we're adding, it takes a ton of energy to launch a rocket and move it a really far distance away. So you're doing work. You're adding energy to the system. It's positive work. And eventually you get to the point where the thing has no energy. So it must have had a whole bunch of negative energy for that to be the case. Okay, so we're doing positive work, we're adding energy, right? And getting eventually to zero. And so we must have been in a negative energy state. They actually call it like a potential well, where you're trapped on Earth right now, right? Like you don't necessarily feel trapped any more than, well, maybe a little bit in your house because of stay-at-home orders and stuff like that. But you're trapped on Earth. You're stuck to it like it's a magnet attracting you, except it's gravity, right? So the statement is what I've been saying. It takes energy to move a particle an infinite distance away to where the energy is zero. So you must have negative energy right now. Right? Out at infinity, there's zero energy since there's zero force. Right? At an infinite distance away, our kqq over r squared becomes kqq over infinity squared. It goes to zero. Right? So let me write that in. Fe would equal at infinity kqq over infinity squared, which equals zero. Divide by a big enough number, you get zero. Have I sufficiently explained this weird thing? With an attraction situation, we've got negative energy, and a repulsion situation, we've got positive energy. Kind of relates to that negative electric field, positive electric field, meaning like attraction and repulsion, right? It's the same reason for it. This is just a recap of it, but the blue curve represents the electric potential energy stored in a system. Notice the energy is always positive. Yeah, the positive is pulsive force. Right? Oh, a positive force, repulsive force. Anyways, and the red curve represents the electric energy. And it's always a negative force, negative energy. Down at the bottom here, I'll just point out that part as R becomes very large. They're both approaching zero, no energy at infinity. This is just a summary of what I've already looked at. Okay, so actual calculations to do with this. We're going to look at an equation for electric potential energy. So to do that, we are going to look at work done. Okay, so this should say delta E, I suppose, right? Delta E, change in energy is work done, right? So that's going to say that here. It's going to say work done equals, well, delta E is going to say eventually, but we know that work done from previous classes in grade 11, work done is force times distance. That was our fundamental definition of work, right? Energy and work was you apply a force over a distance, you're doing work, you're transferring energy. So delta D you could write as R if you want or whatever, right? So we're like, okay, so if the force you're talking about is the electric force, right? The electric force of repulsion or attraction, and the distance you're moving it is a distance r, then that's going to have the same variables in it. So we'd have our kqq over r squared times r. Okay, so this isn't totally true, to be honest, for a reason I'll confess in a second here. But basically, we're looking at force times distance, giving you a logical equation for electric potential energy, kqq over r. Nothing different in that second version of the equation. It's just got the red box over it for emphasis. So just remember here that if we're talking about an attraction situation, it's negative energy values, just like gravity will be. And in repulsion situations, you've got a positive, like it said in the summary there too. Okay. What do I have? But remember, oops, I don't want to erase that part. It's this part. Oh yeah, energy is not a vector quantity. So we're never going to say like, oh, the component of this energy, and based on being pushing at an angle of 30 degrees and so on, they'll add up correctly as far as positives and negatives go, but they're not truly vectors. They're not vectors, right? So you don't have to worry about the direction of them. It's just the value, and that'll come up soon in questions where we'll be able to make that distinction. If I show you this. Here we're talking about vector quantities for forces. So we're talking about components and so on. So they add vectorially fully, whereas the energy concept, if we have a positive and a negative, they're certainly going to work against each other, but they don't have directions in the same way as in a force case.
Mr. Horn.
Yeah, go ahead.
The part was like the negative for attraction, the positive for repulsion. Are we saying that like the final answer is that, or is there like certain things we have to put into the equation?
So we're gonna look at like if it's a negative, like in attraction situations, your energies are negative, and in repulsion situations, your energies are positive. So it's like in here you'll have just put in a red positive plus and minus or whatever, right? So you have a minus plus in here, and that corresponds to the idea of attraction and repulsion. Keep in mind here, of course, that if we had, say, a positive and a negative, you can tell that's going to lead to this one, right? Does that help?
Yeah, thank you.
Yeah. So that's so when you get a result for energy and you see plus or minus as an end answer, that should confirm, based on this, right? This definition along with it should confirm your intuition about what the heck would happen here. We know this is an attraction because we have a positive and a negative. And so we get this negative answer, which goes along with us saying, oh, remember, if the energies are negative, it's because it's an attraction situation. Okay. So this box here confesses that this isn't quite true. At least the result is true, I should say, but the process of developing it is a little bit flubbed. But just like in gravity, so I'll mention this there too, but the problem is the force isn't constant, right? The force isn't constant. So we're not talking about force and work done. So like, let's look at what do I look at? Force, distance, area underneath. Yeah, so force, as you apply a certain distance, they're treating this as if the graph is like nice and straight, right? But it's not. It's not a nice straight graph. Instead, you're talking about the electric force is going to taper off to smaller and smaller values. So let me use maybe a green one here to show what really is going on. And so if you remember from grade 11, we like to calculate areas under curves, right? So this is kind of like length times width here. So this is essentially area equals length times width, and so on. So that sounds great, right? Area equals length times width, and you get your formula and so on. And depending on the geometry and so on, you'd use like the correct formulas for area. But here we're talking about a curve, right? So we're actually trying to talk about the area under that curved surface. And so because the force isn't constant, we're actually finding the area under a curve. So what happens is there's actually techniques that lead to this this equation, right? Truly, that involve calculus. But the nice result actually goes along with what we kind of intuitively think of for just, you know, area under a curve anyways. It's just the product of the numbers. So boom, boom, you get your equation. So it's not, the development isn't truly fully done, but the result is actually correct. So I just thought I'd help you make sure to realize that. And mind you, actually, one of the reasons I'm pointing that out is because pretty soon we're going to be dealing with situations in which the force is constant, how much energy is transferred, and then we're going to look at when the force isn't constant, how much energy is transferred. And so as a student, I found it confusing because it seemed like we were talking about a constant force when we developed the equation, right? But then later on, we're talking about, oh, since the force isn't constant, we have to be careful and deal with it correctly. So I'm just trying to be more clear here and point out, yeah, the force is not constant, but the result works out to be this. So here we go. So find the electric potential energy between a -8 microcoulomb charge and a -5 microcoulomb charge separated by a distance of 2 centimeters. So as usual, you're given some things, you're going to list what you're given, right? What does it say here? Review concepts. Charges are close together, therefore they're exerting a force. Work must have been done to bring them to where they are. Some kind of work must have been done to bring them where they are, right? Whether it was positive or negative, we'll maybe visualize that afterwards, right? So therefore the system's has energy, electric energy to do with it, right? Stored to do with it. More energy stored, whether it was positive or negative, it's still energy kind of stored, right? In comparison to when they were far apart. So you want to picture these charges were really far apart and someone put them 2 centimeters apart from each other. And as a result of that action, there ends up being a positive or negative amount of energy stored. Okay. To sort of cut to the chase here, we've got a negative and we've got a negative. And so we're talking about a repulsion situation. And so it takes work, like let's just put circles around them, pretend they were charges, and actually point charges there. As we're pushing this way, we'd actually have to have an applied force that way, and the delta D is also that way, so you can tell we're doing positive work, right? And so we're storing positive energy in the system, and that's what the energy value is going to end up being because there's 2 negatives, of course. So anyways, once you read a question like that, you're like hopefully in the habit of saying, okay, Q1, Q2, R, they gave me all these numbers. Obviously they are somewhere on this page under the blanks, it's going to say something, but I thought I should point out right away here too, that we divide by 100 because there's 100 centimeters in a meter, giving us 0.02 meters. Meters, kilograms, seconds, always. Page 774 has that metric prefixes stuff, of course, too. So 10 to the -6 for the U, and we go for it, right? They're looking for the energy. So you're saying, hey, I've got a formula for energy. I just learned it today. I'm going to use it. So boom, you plug the numbers in, right? I would have personally had this as times 10 to the -6 in there as well, just to help show what's going to happen, of course. How do I not let go of that thing? I think it's because of the locked page here. There we go. 10 to the -6 and a 10 to the -6. But those numbers, of course, combine and give this. And also, just to point out, remember we have a minus and we have a minus, which led to a plus, right? This plus here, right, indicates, you know, we have positive energy, of course, right? And then you could work the other way around. You could say, ooh, that means that it's a repulsion situation. Which, of course, we'd already know in multiple ways, right? But we have the 18 joules business here. Positive since it's repulsion. Energy was stored when they were pushed together, just to summarize it all and bring it all together.
Sorry, so anytime there's that symbol there, like the micro symbol, do we have to put the 10 to the -6?
Yep. That's what it's meaning. They're saying UC or whatever. They're saying microcoulombs instead of saying 10 to the -6.
Okay, thanks.
Absolutely. So Do I need to stay on that page a little bit, or are we good? Any questions?
Maybe just one more minute, sorry.
No worries. Can you see it well at this stage, or like the way I have it?
I think we can still see it. That's good.
Good. Good to be able to see all of it, even though it's a little smaller.
Okay, I got it. Thank you.
Got it. Good stuff. All right. So yeah, so it's straightforward. They gave us numbers, we plug it in, right? The key later on is just going to be to recognize when you read electric potential energy, you have to have an acknowledgement that this is the equation we're talking about, especially since they gave, of course, these numbers, right? Those values, those concepts. All right, so zooming page width, so it's nice and big. So now we're talking about just a little bit more here, like the work done when we're moving a charge, right? So if a charge is moved relative to another charge, of course, we've been talking about this anyways, right? But work is done to move something if there's a force needed, right? So work done in moving a charge, I'm going to put that in here since a force is needed to do the moving, right? Well, since force is needed. Right, and applied force is needed to actually move it. So you're doing work, so you're transferring energy, So the work done is the change in the electric potential energy. So when you see a question, the reason I'm clarifying that is when you see a question that says determine the work done in moving a charge and so on, really they're asking for the change in the electric potential energy. Okay, so the big concept that is not new at all is change is always equal to final minus initial. So get my screen working again here. Yeah, final minus initial is our usual concepts, right? So I would emphasize that for sure, because that's something that in the context of this new stuff, might not have occurred. That might not have occurred to you right away. But the quicker it occurs to you, the easier this question becomes. These new concepts become, because you can apply the stuff that is obvious to you. It's just you got to recognize it, right? So final minus initial. Well, we're talking about the final energy. So we're talking about the energy. It was moved out to a distance of 4. So that's the 4 centimeter mark, right? So in this, I certainly could still do given, right, and so on. I don't have it written on this page, but I could have. But recognize here, of course, we're going to divide by 100, and end up with 0.04 meters. And so that's the final position. So there it is. There's the energy at the final position. And I'll even show the minus sign, because we're saying like energy, this negative right here is this negative right here, right? There's going to be negatives in there for signs of charges as well, of course, but they're in where they need to go. So that's just your KQQ over R. Notice, I don't know if I'm sure it's obvious already, but when we're doing force, it's KQQ over R squared. When we do energy, it's just KQQ over R. Subtle, tiny little difference. So that's the energy that it has at the final spot. Take away the energy it has at the initial spot. This one does the same thing, of course, here. So this one here, divide by 100. We're talking about 0. Oh, yeah. So we're talking about. I'm going to draw there. Decimal 0.2 is I'm hoping to draw here. 0.02 meters. This is times 10 to the negative 6, of course. So they're actually in there like that this time because I typed it out, and so on. Right, so just plugging in the given information, doing a usual final minus initial gives us a value of negative 9 joules. So what does the negative 9 mean? What does it mean that it's negative? Anybody?
A fraction.
So I know what you mean. Like, so in this scenario, the work done was negative, and so basically we want to think: did we store more energy in the system as we did this? We moved to 4, or did energy release from the system? So we got a delta E, right? I should add that in here too, delta E, E. And so we got a delta E, a change in the electric potential energy. So basically the change is it went, it reduced, right? So this is, the change is the change in energy in the system reduced. So let me add that in. That box down below here is going to have that as well, but energy in system reduces. Basically, think about what's happening here. This is, in fact, a repulsion situation, right? Because we've got negative and negative. We've got likes repel. So as we allow it to repel, if I just let go, if you just let go of the charges, they're going to repel on their own, right? But you've got a negative and you've got a negative, and then they're going out from 2 to 4 in centimeters, right? So it's actually going to repel on its own. What's happening there is energy is releasing, right? So it reduces or releases to kinetic energy. I'll just do EK for short if that helps, if that people still recognize what that means, right? So as the thing goes from the 2 centimeter mark and out, I can ungroup and so on here if it helps. You know, as the thing goes from there to there, it's actually accelerating, it's pushing out on its own, right? You can think of the negative work as if you were holding on to this thing. Here's my arc skills going to come into play here. Ready? So you got your hand, whatever, right? So you got your hand and you're like holding on to this thing and stopping it from going quickly. So picture part of the way along here. We've got the charge has moved to there, you've allowed it to move to there. Your hand would actually be pushing against it in order to have constant velocity, right? That would be an applied force this way. And so as it goes this way, delta D this way, you can picture delta D is this way, and your force is against it, and you've got negative work, right? So either way you slice it, you're getting a negative delta E. Okay, we're getting it automatically from the electrical information. And then also based on the concept of the forces involved, and also based on the idea that energy is transferred out of the system to EK. So what is this back information that's already there? Negative value indicates the amount of potential energy will reduce as the charge moves away. This makes sense since the repulsion force will be converting electric potential energy to kinetic energy. We can even think about conservation of energy. Total energy equals the electric energy plus the kinetic energy, and picture how this one's reducing and this one's increasing. And so it makes sense that energy is conserved. Maybe I'll shrink those down. So how do we feel about that? Should make these arrows the same size. Group, shrink. There we go. Same size-ish. But yeah. Okay, so obviously the energy just transfers from one to the other. Helps you understand, hopefully, the idea. If they ask for work done to move a charge from an infinite distance. Oh yeah, if they're looking at, if you ever were asked for the work done to move a charge from an infinite distance to the location, they're really just asking for the electric potential energy like we saw on the previous page. Okay, so you don't have to do delta E equals E at a distance and then minus E at infinity. So this would be the initial position. But if you did do it, it actually would still work, because you'd be saying, oh, okay, so we're talking about K, Q over R. And so maybe we were asked to move it to a new spot. So infinite distance to a location, let's say 1 meter, right? So move it over to a 1 meter location. You've got your charges, you've got the 1 meter in there, and then you've got your K, Q over infinity. Well, infinity in that equation makes this thing be 0. And so you can tell it's really just the EE equation anyways. Okay, what I'm trying to do is save you a little bit of time where it's like, you can just cut to the chase. The concept that we actually looked at on the first page here and in this first example. In this first example here and on the first page was, that the electrical potential energy by definition is the energy it has in comparison to 0, right? And so in comparison to infinity. Okay, so even though this works, it's certainly not needed every time. It's part of EE equals, part of the EE definition, let's say. Wow, that's really sloppy, but the joys of a touch screen with a little stylus. Maybe I'll redraw that. I have to hold the screen and rest my hand in the right way in order to I'm going to move it closer. So part of the EE definition. Really? Wait. Now it's trying to draw up in lines on me all the time. Need that pointer tool, I guess, with the mouse. Anyways, so that's electric potential energy so far. And to do work done by moving charge, you find the change in potential energy. So when you have electric potential energy with multiple charges, this is where the vector idea won't matter. Okay, so we're talking about the electric potential energy stored in a system of charges. So in this case, we've got 3 charges in a little right triangle situation here. If we were talking about forces, right? If we were talking about forces, so for example, here we might look at this situation and say, okay, we've got a force from this one. We're not talking about force right now, but I'm just showing you to compare with what we've done in the past, right? So this would be the F of 1 on 3, and then we'd have the force this way, I suppose, of F of Q of 2 on 3, and this would be vectors, right? So just in contrast to that, we're not going to need those angles. We're not going to need vector addition components and so on with energy. But the negatives and positives are still going to matter, but it's not going to be in a vector way. So yeah, the positive and negative values of electric potential combined, essentially they're going to subtract, whether, like if you have positive energies and negative energies, they're going to subtract to give the total energy stored in a system. Okay, so I'm just trying to wrap your head about what we're talking about here, and we'll start looking at steps. So first step, we are going to need the distance, right, in order to get this R value. So this is the R between 1 and 3, right? So we're going to need that value. We're going to need Pythagorean theorem to get that, and this was given as a right triangle there. It just wasn't obvious. On a test, I would have to give you that 90 degree, of course, so you know that this is what we need to do. So I've called it X on my original work there. So I'm going to say X equals that R1 to 3 distance, right? So 2 and 1, and now this is 2.24 meters. Okay, so we've got the distance. And I had just a more an idea step here, right? Since electric potential energy is a scalar value, we just add up all of the energies associated with the different combinations of pairs of charges. That's an important concept to recognize, right? All of the different combinations of pairs of charges and the energy associated with them. So energy associated with all of those, we need to add up all of those. So if you think about the energy associated with 2 and 1, the energy associated with, so let's start actually from this one corner. We'd have the 1 and 2 combination, the 1 and 3 combination, right? If we then went to the 2 charge, if I said the 2 and 1 combination, we already talked about that one. The only one left would be the 2 and 3 combination, right? So it'd be like the 1 and 2 and the 1 and 3. And then from here, you'd be left saying, oh, the 2 and the 3. By the time you get to the 3rd charge, you've already talked about all the combinations, because you've already talked about the 3 and 1, and you've already talked about the 3 and 2. So how that looks here then is what? Let's go actually this way. So the different combinations of pairs of charges, of course, we're going to have about 1 and 2, 1 and 3, and then 2 and 3. Okay, you're adding up the energies. I have blue add signs there on purpose. You're adding up energies. Please don't put negatives in. Don't look at it as like, ooh, this one's going to be a negative energy, so I'm going to put it in as a minus. No, let the charges determine that for you. Okay, so you're adding up forces. Just like with net forces, it was always F net equals all of the forces added up. Whatever blank plus blank plus blank, right? We didn't in grade 11 say, oh, blank minus, like say the applied force minus the gravity force, because we know it's going to be down, right? We just let the negative G make it be down, make it be a negative. So we end up adding negatives, right? So what do we have? This one is going to end up being a positive value. You can see it in here. There. Right? Because we've got 2 positive charges, right? So that we know means repulsion. That's a repulsion situation. These other 2, so that was Q1 and Q2, repulsion. The rest of them are going to be attractions, I guess, right? So we got an attraction situation. Those are actually going to be negative values. So there's a negative and a positive in the middle one. Right, you got a negative and a positive, so that's going to end up being a negative in the bracket, and again here a negative and a positive as well. So like I said, we have the energy from the one plus the energy from the other plus the energy from the other. So if I still had these as blue, maybe that would stand out. We're still saying like all the energies added up, right? The signs are going to combine logically, but we don't call those vectors. We just say the positive energies and minus energies are adding up. So it actually adds up to be negative 6.62. Okay. So if it's negative 6.62, then you should recognize that that's an attraction situation overall, right? The overall combined energy of these is an attraction situation. We got a potential energy of the system of negative energy. Overall, actually, I already said it here, right? I've got it listed where it's like overall, this is a what kind of system then? We know that, of course, that it's an attraction situation. And think of it as like the positive and negative charges being close together. We've got this positive and negative charge here. So let me highlight with my purple here. So the larger positive charge being close to that negative charge kind of is why you can see that the math concludes that these guys kind of take over and make this an attraction situation overall. The repulsion aspect of it is farther away. So first glance looking at it, you might have thought it'd be a repulsion situation overall, right? Because you've got 2 positives and then you only have 1 negative, but I guess you've got a negative attracting to both of those positives, however you want to look at it, but the distance between does matter too. I just think that we have the luxury of being able to analyze it after the fact and say, okay, that makes sense. Okay. So hopefully you're getting comfortable with just firing these weird numbers into your calculator. You got like your 2e5 negative plus, times 4e5 negative. Like that shouldn't be a stumbling block for you. It's not like we're asking you to do all this calculation by long division and on paper or whatever. So fire into your calculator and get numbers. Any questions at this point? So the previous lessons that we've done were kind of like, they would have been like a 2-day affair in class. This is just a 1-day affair, so we're heading on to the next one. But before I switch to the next lesson, of course, you will see the questions that I've picked out that are good for you to do. In number 18, huge time saving hint there, consider common factoring. Instead of having so many numbers, all the time to type into your calculator, and just a you know, you get carpal tunnel syndrome going through it. Notice that there's a 9 and a, you know, anything you could factor out of here in this situation, the common factoring isn't as beneficial because you've got like different combinations of charges. But we could have common factored that 9 times 10 to the 9 and got all that stuff and then just multiplied by 9 times 10 to the 9 once. In this question in the homework, it's a huge benefit because the charges are all identical. So you can actually common factor out the K and both the Q's out front and only type 9 times 10 to the 9 and whatever the number is, 3.2 times 10 to the negative 6, you know, and so on and so on. Type those in once only. That's a huge time saving hint. The other time savings hint from that one is, remember that it's only the combinations of pairs. So you don't have to worry about, you know, 1 on 2 and 2 on 1. You know, 1 and 2 is a 1 combo, is one of the pair combos. I almost took this question off the list because when I first looked at it, just to help you understand what I'm talking about here, I think it talks about a rectangle. And then you have charges and so on. And so I originally, when I first looked at it, was thinking, oh my God, we're gonna have to talk about this force and this, so that force from there. If they're all the same, right? So it's all repulsions, and that force from there, and that force from there. Do all those calculations, and then force there, all those calculations, force there, all those calculations, and so on. So many calculations. Now at least there would be a lot of symmetry, but still a heck of a lot of thought process. You don't have to do all that. Okay, in reality here we've got energy to do with how many pairs. So we'd say call these 1, 2, 3, and 4, let's say. So you'd have the energy combination between 1 and 2, 1 and 3, 1 and 4. So there's certainly 3 to start out with. But then when you go to the red, the 2 here, 1 and 2 is already taken care of. So now you have to just talk about 2 and 3 and 2 and 4, right? And then when you go to here, finally, you're like, oh, I already got the 4 and 2 combo and the 4 and 1 combo. All I have to talk about is the 4 and 3 combo. So there ends up being 1, 2, 3, 4, 5, 6 pairs. So you've got EE equals 1, 2, 3, 4, 5, 6 of them. Still random, but anyways, yeah, 6 of them. Okay, so that just to help you see that equation is going to be a lot easier that question is going to be easier to do than it might look at first, especially if you're thinking forces like I was, because then you have to think about every single one, right? Whereas this is just pairs of energy combinations, K, Q, Q, and then it basically becomes over R, over R, over R, right? 6 of those, right? So that's a lot of help on that one to help make sure that's not a major time user of your day. All right, so that's 15, 16, sorry, that's 16, 17. So 17 is, yeah, we'll have to be careful here because there's some little distinctions that seem like contradictions of what we've said in the past, and I'm going to deal with them very carefully. Unlike I recall seeing when I was in school, and also unlike this textbook too, they don't distinguish. And I'll just tell you right up front, the distinction is in your training and what you've seen so far, voltage means like electric potential difference, and that's still true, right? But I remember in grade 11 and 9, or 9 anyways for you guys, if someone wrote delta V, it was kind of like saying, oh, the difference in the difference. And so we didn't write that. But in grade 12 physics, we do write delta V, and I just need to draw your attention to that and make sense of it and analyze why it does and what the context is, what we're talking about. Okay, so that's part of what I'm going to mention here is that delta V actually makes sense in this context, and it's not a contradiction to what you've seen in the past. Okay, so just watch for that when we get to it. So and it's going to happen pretty quick. So to start it with here, a new definition for us. We've talked about electric force, we've talked about force per charge, we've talked about energy, and now we're talking about energy per charge. So just try to keep that straight in your head, right? We've talked about electric force. I don't know where I want to put this on this page, but let's just do a little pre-page here. We've got electric force, check. We've got electric force. We've got electric force, and basically that should be like check. I'm good with that. We've got electric force per charge, right? Which was curly E. And we're like, okay, yep, I'm good with that. We've got electric energy. So, yep, we've done that. You're going to do some questions to do that soon, whatever. We just assign those. And so now we're talking about electric energy per charge. Okay, that's the progression of concepts that we're dealing with. Force per charge, energy per charge. Kind of makes it easy to see. Okay. So energy per charge is electric potential. So let me maybe jot that onto this list, of course, right? But this is electric potential. So just you're going to read a question soon, and it's going to say, oh, the electric potential is blah blah blah, and you need to recognize, ooh, that just means energy per charge. Okay. So the fancy name for electric potential energy per charge is just electric potential. So notice that we're using that symbol volts, right? So we're using the symbol volts. That's the symbol for electric potential. And this is where you might start to say, wait a minute, in grade 9, we said volts was electric potential difference. Okay. And notice in the headings for the lesson, we're going to be looking at electric potential, and we're going to be looking at electric potential difference. So I hope right now you're with me and saying, okay, wait, what's the contradiction? What's the solution to this apparent contradiction? There is one. Okay. But let's just go with this for now. We're saying this is electric potential, and it is volts. So it's what did I say? It's not really much more complicated than energy. It's just energy per charge, right? Part of the reason this is mysterious to us is because we don't talk about energy per charge with gravity. Okay, we only see this electricity, so it's unfamiliar. If we're in the habit of talking about like gravitational potential energy per mass, then this wouldn't seem as confusing because we would have already gotten good at it with gravity work, right? Especially if I taught the course in the more traditional order of doing the gravity stuff first. But either way, we don't actually do it anyways, so it doesn't matter. But yeah, so like gravity energy per mass isn't a concept that we list and work with, but we do with electricity. And I think it's because like you can have so many different charges in so many different situations, whereas usually you're talking about gravitational potential energy relative to Earth, right? And so it doesn't the masses don't change very often. The mass that you have energy relative to is always Earth, or quite often Earth. So I wonder if astronauts tend to talk about energy per mass more, right? Think about it. An astronaut goes to a new planet, right, or a new moon. So then they would notice the energy a brick has is less on the moon, for sure. You drop a brick on your foot on the moon, it's not going to hurt as much because there's less energy per mass, right? So that's a very valid concept for an astronaut to work with more than non-astronauts. All right, so electric potential energy, we know it's stored due to the work that's done against the electric force to move a charge from infinity to a location. We're going to start to deal with this contradiction. Okay, so we're talking about electric force moving a charge from infinity to that location. That's the EPE, right? The electric potential energy. So picture this diagram here where we're moving a positive test charge from infinity to this spot. That's work done, of course, right? So that is yeah, I should add in here. They should have had it added in here. If they're going to say electric potential, this should have been work done per charge, right? Per Q. And so in other words, it's electric potential. Electric potential is equal to the electric potential energy per Q. So a little correction needed there from the textbook scan. Yeah, so electric potential energy per unit charge, or simply electric potential, is the amount of work necessary per coulomb of charge to move a charge from infinity, which is where you have zero energy, to a spot, right? To a point in the electric field that's produced by some source charge. And we're going to make that contradiction more obvious soon here too, or we're going to fix the contradiction. Because I hope you're still looking at, wait a minute, I thought V equals potential difference. Right? So if you remember that voltage in grade 9 was potential difference, now I'm just calling it electric potential, and soon I'm going to talk about electric potential difference. You should be saying, well, wait, I thought it was difference. Okay, this one's just the value, okay, rather than the difference. But we'll fix that shortly here. So electric potential, what do we have here? Is electric potential V is electric potential energy per unit of positive charge. Yeah, so 1 volt is when you have 1 joule per coulomb. It's going to be positive for repulsion as normal and negative for attraction. I'll let you copy that down. All right, so hopefully you're sort of thinking that there's an equation that's going to be pretty easy for this, right? Since we got electric potential energy is KQQ over R. Now we're talking about energy per charge. It's like KQQ over R divided by Q. Those Q's are just going to cancel out. So an equation is actually pretty easy for this one. Any questions about this page though before we start with? We're just saying it's energy per charge. And so it's the energy per charge that it takes to move it from infinity to that spot, right? So this is that apparent contradiction part. Voltage in terms of electric circuits and so on was the change in the electric potential energy, or in other words, potential difference. With the new term that we're talking about, electric potential, it is actually still a difference. Okay, difference is still part of that concept, 100%, but we don't say it because it's a difference between the energy per coulomb at the location in comparison to an infinite distance away. At an infinite distance away, the energy is 0, right? And so what we're saying is you can just refer to it as electric potential because the result you have is the same as the change. Okay, so I'm going to come back to this page probably in a second, but I'm just going to put it in simple terms for you here. Think of like the gravity potential energy stuff. We talked about this in that one. We talked about how we could call it delta EG if we want, but since we're comparing it to a 0 level at the floor, we just called it gravitational. So if I lift something, give it 20 joules of energy, right? Lift this box up to here, 20 joules of energy, then it has 20 joules of energy relative to the floor. So we could call it a delta EG because I gave it 20 joules. But since we're comparing, to 0 at the original level, it's the same as just saying that's the gravitational potential energy it has, rather than thinking it was a difference. It is a difference because it was the difference from 0. In a money sense, I'm still sticking with the gravity one, I guess. So energy per mass would be the same concept as electric potential, and so we would have had EG. We've had EG would have been energy per mass, right? I should have showed this page after I did the equation one for electricity, but it'll make it seem even easier, right? So in a GMM over R equation for energy to do with gravity, it develops the same way as the electricity one. We'll see that it's easy. But so instead of being GM over R squared, it's GM over R. So it's energy But yeah, this is the big M's the mass of the like the Earth or the big mass that you're comparing to, and then the little mass, like you, for example, stuck to the Earth. You know, that energy per your mass just becomes GM over R, and so that's the gravity potential, the gravitational potential energy per mass. The money example I wanted to mention. Did I not have did I not leave the money one? Oh, maybe it's down here. Yeah, sorry, another example. I just missed where it was. If you had no money and you gained $20, then the difference in your amount of money is 20, right? But it's also your actual amount of money, right? So if you have no money at all, someone gives you 20 bucks, the difference that day is 20 and your actual value that day is 20. So you can just say, I have $20. You don't have to say I gained $20. You can say I have $20. They're the same, right? So your difference and your amount of money they're actually the same thing. So you don't need to say the difference part. That's what we're talking about, right? Up here, this idea of electric potential, this is a difference, certainly, right? From 0 joules out to here. Now we've got a certain amount of energy per charge, and we're talking about, you know, it's the energy which is equal to the change in the energy per charge, right? So if this took, you know, 100 joules to move it into place, right, then it has 100. The change is 100, so is the value. Okay, so that's why electric potential is talked about as just potential, period, not saying difference. It's just sort of, you know, difference from infinity, but, you know, who cares, because at infinity it's 0.
Can you zoom in on the diagram? It's too small.
Yeah, sure. Let's do full page, maybe, view, full screen. Is that a little better? So we've got a charge that's causing a field, and then we've got a test charge out here that has been moved from infinity in. And so at infinity we have 0 energy, and let's say 100 joules of energy. See if I'm still drawing. Here I am. 100 joules of energy was added to the system to move it to here, right? Especially if this is a positive and this is a positive, and we can just talk about positive work done to push it into place, right? So it's a positive test charge and a positive charge, repulsion situation. We've got positive energy. It's easier to think of. So we've added 100 joules of energy to the system. It actually has 100 joules of energy per charge, right? So, you know, the difference in comparison to infinity is 100, but the actual potential it has per charge is 100 also. So we don't need to say difference in comparison to infinity every time. And so that's why we're dropping the difference word for now and saying we're just talking about the potential, right? We're not talking about the potential difference at this point, even though we really are. It's the difference in comparison to infinity. Good. All right. Long enough for the zoom in there. Yeah. So this idea of it still is like I could add in here. This is actually difference in comparison to infinity, right? Electric potential difference in comparison to infinity, but you're probably better off just to sort of understand that rather than like write it every time. So yeah, so according to the definition, then we're talking about energy, electric potential energy per charge. And so we're saying electric potential energy per test charge, right? And so we're talking about the electric potential energy equation that we just dealt with from the first lesson. Would have been yesterday's lesson, but quadmesters are great, according to someone. I won't say anymore because, you know. Yeah, so they have the electric field would be, or electric energy, sorry, would be the K value, the 9 by 0 to 10 to the 9, times the quantity of the charge is causing the field, times the quantity of charge that the test charge is, divided by the distance, you know, between the two things, right? But now we're talking about that electric potential energy per that actual test charge. So you can see here, test charge divided by test charge is going to cancel out. So we have electric potential. The equation is just KQ over R. Okay. So you have the concept of potential, energy per charge. This one here, I would say, is the concept more so
you know, it's the equation to do with the concept directly. It's like kilometers per hour, you know, for speed, right? It's energy per charge, the concept to do with potential. And then the equation here gives you like the how to calculate the numbers, right? So numbers for it based on the actual charge and the actual distance and so on. All right, so again, since energy is not a, it's a scalar concept, it's not a vector quantity, you know, our positives and negatives are going to add appropriately, but we're never going to have to worry about like the component of the potential and so on. They're not vectors, they're scalars. Okay, so you're still going to have positive for repulsion and negative for attraction as usual, because a plus and a plus means repulsion. A minus and a minus means repulsion. So that's these cases, in case anybody's quietly been wondering, like, how do you, you know, if you ever forget that, just remember, if you have a plus and a minus, then you're going to have, oops, I better draw them a little further apart so I have room to show attraction. But if you have a plus and a minus, then we've got attraction forces, right? So a plus and a minus in your Q's, right, would lead to a negative charge overall. I won't do that because that's ugly. But yeah, right? So a plus and a minus. Let's do plus, minus, you know, leads to minus, of course, right? And so on. So hopefully that little clarification might have helped if it was needed. What do we have? Remember the test charge? Yeah, the test charge is the charge that's feeling the effects of a field. There was a field. There was a question in the homework about why do test charges have to be small, right? They have to be small because they don't want to affect the field itself. So these are small, and so they're not contributing to the field itself. They're not changing the electric field. So they are very much a theoretical thing. A test charge, you know, you put a test charge in the area and see what kind of force. We're doing that in theory more than we're doing it in practice, right? But it's pretty obvious, right? I can test the force of gravity from the Earth by measuring the force on a mass. Is that mass that I'm testing the force on affecting the gravitational field in the area? Not by much, right? So that's the same idea. Questions about the equations? Couple new equations to think of, right? So potential is, you know, electric potential. This is the equation that we're doing here. This should be a little bit more of a highlighted in name, but electric potential, we have V equals EE over Q. Potential equals electric potential energy per charge. That's the concept. And then the resulting equation is KQ over R, since we know the equation for the electric potential energy. All right, so there's a new equation, there's a new question to practice. So it's just, what's the electric potential at a distance of 0.9 meters from a charge? And you're just plugging the numbers in. Like it's, you know, they gave you the charge and they gave you, that's the one that's making the electric field, right? And then they gave you the distance. And so they want to know the potential. And so you just plug it in, right? So I'll just give you a chance to maybe jot down the numbers, but they're going to be, I'll just move it to there at least anyways. So yeah, you're just going to use the equation, KQ over R, plug in the numbers, use your calculator, get a value. So the potential is -3 times 10 to the 6 volts. Remember, volts does mean joules per coulomb. That's the same as grade 9, right? It's just we're not thinking this as meaning difference as much in this case. We're not saying potential difference. We're saying potential, period. Right? It is a difference from 0 at infinity, but that's just kind of not needed to be said every time. So it's not part of the definition. So electric potential is that much. I put there that's negative since it's an attraction situation. Energy was released when the charge attracted from infinity to that location, right? I can even add in the note that the energy energy decreased by, I'll write out that number with my pen maybe, from 0 at, move that up here. So that's the idea of the whether it's a difference or not. That'll work good. So what I want to have in there, of course, is that value. I'm just going to grab that part right there. So it decreased by that amount, right, from 0 at infinity. So you end up with -3, you know, a difference of 3 times 10 to the 6 in the negative direction, a decrease. So you end up with a value, an actual value, rather than just a difference. Okay. And that's just a simple case where you're talking about what's the electric potential at a distance from. So basically, what's the energy per charge at a spot, and it calculates out just like that. Okay. I don't feel I need to do this at this point, but more about the plus or minus. What do we have there? Oof. Electric potential energy is negative. In other words, 1 coulomb would have that much energy, a negative energy at that position, in comparison to 0. Yeah. So that's really what I was talking about. It lost energy because it transferred to kinetic as it came in from infinity. A positive charge, of course, would have positive potential. In comparison to infinity. So, are we ready for this? So in your own words, explain what's meant by electric potential. In your explanation, relate the work done on the charge to its electric potential and explain how a charge can have a negative potential. You know, maybe I'll just get you to think about that. I'll reveal the answer so you can see it in the PDF. But you know, you gotta think about what your answer is going to be based on what we did, and then look at those later on and see that you've accomplished the goal, right? That you can describe it. Okay. So the last bit is to actually tackle that. These go as a part and parcel pair here because we got to be able to compare them, right? So now we're actually going to talk about electric potential difference. Why we're going to say difference in this case, okay, why we're going to say difference in this case is because we're going to be talking about the difference between two, I refer to it here as like local positions. So we're going to be talking about, if we went back to this one, I might say, you know, between X and Y, here we'd be talking about potential difference. Right? Because we'd be saying, oh, how much of a difference is there between these two spots? But this one here was just electric potential, period, because it was a difference with infinity. Okay, so this one is just potential, and then this one between there and there is going to be delta V. It's going to be potential difference. Do you follow me? Hope so. So when we talk about potential here, technically it is potential difference, but it's just difference from that spot in comparison to infinity. Now we're going to be talking about two local spots, X and Y, you know, for example, in that question. So what do we have here? It requires work to move a test charge. Yeah, work is required to move a test charge or any charge, whatever, right, from one spot to another in an electric field. So point X to point Y. That work is equal to the electric potential difference, right? As long as you're saying per charge. So if we have an electric field and we're moving from one spot to another, this curved line here, I'll explain why they're doing that. But basically we're going from A to B, or it was X to Y in the previous question, no big deal, right? So moving it from one spot to another, the work done there is your delta E, right? So the resulting delta E. So the resulting delta E, right? You know, goes into a calculation and gives you delta EE per Q. That's your potential difference. Okay, potential difference is delta V. Okay, why this diagram of this path that's curved and so on? That's because electric energy and electric fields and so on, the forces they're called conservative forces. And so the path you take and going from one spot to another doesn't matter. If you're lifting a brick up a meter, doesn't matter whether you zigzag side to side. Once it gets to a height of a meter, it has a certain amount of energy, regardless of the path you took to get there. Right? Same thing here. Doesn't matter what path you take. You get from location A to location B. The potential difference is the result of the new R value. Right? So we would have had, there would have been a big Q over here, let's say. I'm going to use a cap. Well, I don't know if I should use capital or not, but anyways, we have the charge. Right? So I'll switch back to the little q because we always use it. But it will make it big. And so this Q is causing an electric field. So let's make those something. Okay, so we have a Q causing an electric field. And now we're moving from point A to point B in it. And of course, we've got a distance, right? So we've got a distance of let's call it like RA, distance from A, and then RB, distance from B. Just for now, I'm going to label it like that. But and then, so of course, you could find the difference. So that's what we're talking about. We're talking about difference between two local spots. So clearly, we still know that any difference, right, is a final minus an initial, right? So delta anything is final minus initial. So we're talking about the electric potential energy, you know, at B, the final spot, minus the electric potential energy at A. Okay. So I put on there, recall, of course, that potential is energy per charge. And so we're saying, oh, well, I have to show that sort of here, just like this. Since if we're going to talk about energy, we're going to actually say QV. We're just going to solve our new equation that we talked about for potential. We're going to solve it out and get energy. So now we can say energy final minus energy initial, or energy at B minus energy at A, so is all this really is. EB. I should maybe say EE at B. EE at B. Subtract EE at A. Right? So we got the electric potential energy at each spot. So that way we're not talking about the energy per charge anymore at this point, just to get the difference in the energy, right? But anyway, so our energy is Q delta B. Okay, which means we're going to be able to say, oh, okay, so then potential difference is delta EE per Q. That's going to be the equation on the next page as well. Just follows directly from this one, so I may as well show it now while we're looking at it. So all we're doing is using the potential idea. Notice that we're saying in purple, maybe here to compare, or green, in comparison to infinity, right? This one has a certain amount of energy, and this one has a certain amount of energy. The difference between those is the delta V, the delta E, and then the resulting delta V, right? So it's 0 joules at infinity, a certain amount different to be at A, but that's the actual value, a certain amount different to be at B, but that's the actual value. Now we can talk about the difference between those and talk about potential difference between those two spots. Questions about that? The idea of the path doesn't matter, isn't that critical, it's just true. So yeah, so there's the equation I said that was going to be on the next page. Electric potential difference is delta V equals delta E over like the change in electric potential energy per charge. And again, we're not talking about vectors, just the signs matter, but yeah. So just as a recap, electric potential is V equals delta E over Q. Electric potential difference is delta V equals delta E over Q. Right? And then these are both actually differences, but this one's just different in comparison to infinity. So I'm not going to leave this here, but this is like delta in comparison to infinity, delta in comparison to infinity, right? This is what's true, but I can't leave that there because it would be misleading if you see it written as delta later on. Okay. So I do have that written there. Difference relative to 0 to infinity for electric potential, difference between two local spots for electric potential difference. So we already had that new equation written. Let me know if you need anything. All right. But to make this even more confusing, thanks to your textbook authors, they often write delta V as VBA or VAB at sort of random. Think of VBA or VAB as like a subtraction between the two. Okay, so that's a notation thing that you're going to see. So for example, in a parallel plates example we're going to see tomorrow, they list this as VAB. VAB is in fact a delta V. Okay, so we are now showing voltages applied as delta V's, even though in grade 9, we tried to simplify things a little for you, right? And just call it V. Okay, so we are talking about delta V's now. So delta V, the difference between these two spots, right, is one take away the other, of course. So that's how that ends up looking in use. So just make a note of delta V being the same as, you know, VBA or V12 or VXY, you know, difference between two spots. So that does mean potential difference, good old fashioned voltage. Yeah, that's the textbook way. Them writing VAB or VBA is their way of acknowledging the confusing sort of inconsistency between V in grade 9, right? And then delta V now in grade 12, in 4U or whatever, right? So a 9-volt battery previously would have been written as just V equals 9V, but now we're going to say like VAB or delta V equals 9 volts, okay? Which obviously we did refer to as potential difference. So everything is consistent, just hidden almost, right? It's hidden that this is a delta in grade 12, I should say. Hidden that the one we talked about originally was delta. Up here in the pages, wherever it was. Up here, yeah. Somewhere up here. Potential, yeah. Hidden, that's a delta. Because it's in comparison to 0. So at least there's a reason for it, right? So what do I have here? For point charge Q, the electric potential difference between two spots can be found by subtracting. That's just what we've already done, right? So, that is a little bit different actually. So we're saying delta V would be the potential at B minus the potential at A, like final minus initial kind of thing, right? The way my arrow is written there, final minus initial means I should have had the arrow like that, I guess. So going from A to B, final minus initial, you can picture your two equations, your KQ over R at B, the final spot, minus your KQ over R at A. And so this is that, maybe of that, reminds me of that common factoring I was mentioning you can do. But you can just picture how you might work with the equations, of course, as you go through this. So going back to this page here, we had electric potential in comparison to 0 joules at infinity, right? So technically this is V equals, right? But technically, because it's in comparison to 0, it is a, let me go with green, right? It is still, let's point out it's a difference in comparison to 0 to infinity. So technically we can put a delta there, right? Like sort of, and if we know what we're talking about, but we're going to just call that V. And then finally, the new one now, and finally we've got delta V, for sure delta, which is now delta E, electric potential under delta E per Q, right? And so this delta is like a difference between two local spots. Let's say like spot A and spot B or something like that. Right, a local local delta, let's call it delta D, I guess, a local spot, local difference. I don't know what word you want me to use there. Local change, let's say. Okay, so summary page here, FE, right, for electric force per charge, electric energy per charge in comparison to infinity, and then finally change in the electric potential energy per charge between two spots. And so that clearly applies to circuits, right? We're talking about either spot of a battery in a circuit. We're talking about point A and point B on either side. Like this is really what should have been used in grade 9, but you can kind of respect why we wouldn't have tried to subject grade 9s to this. Just not ready for it yet, conceptually. So here's a question. Where I got this question from, it is what it is, but the order of this question really should have been A, B, and then D, because once you have A and B, D is very doable. So we'll do that. But electric potential at a spot, that's just your energy per charge, right? At a spot. So that's the one where it's just the source charge here, right? Notice that you might get they're it's fine. I thought they were giving you another charge, but they're not. So what's the electric potential at a distance from a charge, right? So two different distances, two different values for electric potential. So we want to know V. We know V equals KQ over R, which conceptually we know is EE per charge, right? But we're not using that formula because we don't have the energies. We don't have that. Anyways, the given numbers go in, calculate a value, there's your potential, which is joules per coulomb. And of course, the same process for the other spot, for the 10 centimeter spot. We end up with 2.3 times 10 to the 5. Okay, so we got electric potentials, energy per charge, in other words, at these two spots. Just like that. Okay. So each of these has a positive value, which shows that it's a repulsion situation for positive test charges, at least. I should add in for test charges. But that's the whole point, right? It's like in comparison to a positive test charge, is the energy positive or negative, and then you can analyze based on that. Like in that homework question where it said for a negative charge, the force is to the left, we ended up saying, oh, that's because the field is to the right. So that just gives us the electric potential at each spot. And then if we skip to D, D says what's the potential difference, electric potential difference? Well, that we just want to subtract those two numbers, right? That's just the difference between the two. So literally you could just say, well, it's the potential at one, take away the potential at the other. Potential is always, or difference is always final minus initial. So we just subtract those two numbers. So we get delta V equals 1.8 times 10 to the 5 volts. Okay. So that would indicate that a force, that energy was required to push a positive test charge inward. A force was required to actually push in that direction, to push it inward, right? Whereas, and the potential increased as it was stored. If it was a negative value, that would indicate that you're like trying to stop it from going in, right? Or stop it from initial position. Yeah. So we're pushing inward. So you'd be trying to stop it from going in if that was a negative number, right? I could add that in. Versus if it was minus 1.8, right? That would be if we had a negative Q situation. So negative Q situation, a positive going from 50 into 10, you can tell you'd have to try and stop it, right? And so we could say, obviously, energy would be released to kinetic because it would attract. And so EE would transfer, EE would transfer. Come on. I don't want to do all that, so I'll erase instead. EE would transfer EK. So in other words, this one would decrease, of course, right? So that, yeah, so, and the idea of the charge itself here, the positive test charge, we'd have to, I drew with my hand before, remember? So there's my hand or whatever. You'd actually have to have an applied force this way as it goes this way. Right? You'd have to be holding it back in order to have velocity equals a constant value. Whew. So if it was a negative there, that's what that would mean. So I'll come back to number 2 here after doing part C. Okay, but part C said, what's the amount of work that must be exerted to displace a specific charge now? So now we've got a negative 2 times 10 to the negative 3, so smaller than the other one, right? Because it's not supposed to affect things. So we've got this negative 2 charge now. So Q negative 2.0 times 10 to the negative 3, right? So that's why I wanted to talk about what happens in a negative situation. So you've got this negative charge, it's going to want to attract to here. It's going to accelerate on its own to this spot, right? And so if you're holding it back and letting it go slowly, you would have done negative work. Or if you let it go, then negative work, the reduction in the energy of the system, transfers to kinetic. Okay, so that would look like this. So to find the work necessary, we got delta V equals delta E and so on. And basically we need to recognize that delta E is that concept we're talking about, right? So they're saying here, since work delta E, of course, right? So if we rearrange that, we can of course get the work value. So Q delta V. And then the delta V is that change that we already did in part D. That's why it's annoying that they have this as part C, because you actually need to do it to get to part C. Anyways, so that change that we already got was that negative, oh yeah, there's the, I didn't give the value, it's still that subtraction, right? But there's the charge we're talking about moving in and so on. So there's that 1.8 value, and so we end up with work done is negative 360. So 360 joules will automatically reduce from the electric storage energy that's stored out to kinetic. So the work done to move that is negative 360. And it's an attraction situation, right? This motion would happen naturally. We'd have to apply a force against it to stop it from just going like crazy and doing its thing. Also could point out the E total thing, right? E and plus EK. And the change, should point out delta and delta here, right? So this one's a minus 360. This one's a plus 360 because the energy went to it. And of course, you've got the total energy, the change in the total energy is 0, right? Overall. So I'm just trying to connect as many dots as I can as we think about this. Negative means it's energy coming out of the system, going to kinetic. So that should make sense based on the new equations once you get used to them. You know, it's recognizing delta E's work, and we already have that delta V value, so we can use it, right? We could have just gone from scratch and said, well, let's just calculate the electric potential energy. We already did that in the previous lesson, right? In this one here, in 16, I guess, right? We talked about electric potential energy. So why couldn't we just do that? Well, we totally could. It's just now we're using that new concept, right? So the electric potential energy stuff would just be Q over R at one and at the other, and subtract them, and boom, you know, you get the same number. So this is from the previous lesson, but it's just connecting the concepts together. Okay. So if you're just using electric potential energy straight out, well, that's fine. But this is using the concept of electric potential rather than electric potential energy. Okay. I just put here the direction wasn't obvious, so it could have been going the other way, in which case it would have been a minus and so on, but we've already analyzed out the minus case, so I'll skip that. So that's pretty much it. They do ask another question here that I can leave for you, or we can go through. But this, think of a situation where you're talking about a positive test charge would repel away from A to B and so on, and they ask like, is work done to move from A to B, positive or negative? And so if the charge is a negative charge and we're moving away from a positive, I think, yeah, from a positive, then that would be positive work because it would want to attract, and so you'd be doing work to push it away, right? So think through all of those things. I'll make sure to reveal these so you can see them in the PDF. But on your own, you might want to sort of try not to look at the answers. Maybe what I'll do to make that easier for you is I will clone this page and reveal the answers on the second page so you can actually look and check the answers. Just conscious of the few-minute time warning to the end of the, well, before the final half hour of our class, technically. Okay, so again, questions are at the top here to do with electric potential and electric potential difference. And the solutions are all going to be posted right away, so you can refer to them as you try to do stuff. I'm definitely hoping that's helping you. All right. Okay. So I will stop recording and post that stuff for you.